So the idea today will be to share with you some ideas about open science in general, about the question of reproducible research, that is the ability of our research to be reproduced and verified by others. And in this context, what is the position of articles, code, data, and the reason why we should publish code and data the same way we publish articles and cite them. So that's going to be the whole thing. Open science is a pretty large subject, and I'm not going to cover all of that. First of all, because I'm not competent enough on that. There are lots of resources available out there in the web that you can find on this subject. Also, it's a set of practices that can be implemented in lots of different manners. And in this presentation, I will specifically focus on how we can implement this in our community, in computer sciences. What I say might be true for some other domains, but it might not. So maybe in, I don't know, in the humanities, they will use different ways of implementing open science, and this is okay. I mean, there are probably different ways of doing it. Also, so I will have a brief introduction on open science, and then I will focus more specifically on the question of reproducible research and how we can achieve this. And I'll show why code and data are outputs, research outputs that are necessary to achieve reproducibility. Then I will get into a bit more details about how we can make our software, our data, findable, accessible, referenceable, and citable. I will describe these terms. And in the end, I will take the things the other way around. That is how, if once we have our code and data citable and referenceable, how we do cite and reference the works of others, not only their articles, but also their data and code. So let's start with an introduction on open science. So, there are many definitions of open science. I've taken one that comes from the second National Plan for Open Science in France, the PNSO2 en français. And it reads like this. Open science is the unhindered spreading of the results, methods, and products of scientific research. It is based on the open access to publications and, as much as possible, data, source code, and research methods. So, in other words, what it says is that articles, data, and code, that is the software we produce, should be accessible publicly under open licenses. They should be, to do that, I mean, to make them open, they should be made findable, accessible, reusable. And when I say that, of course, you think about FAIR. FAIR is this acronym that has been around, I think, for 8 years maybe now. FAIR applies specifically to data, and it says that open data should be findable, accessible, interoperable, and reusable. And actually, fairness, we speak about fairness of the data, is clearly a part of open science. But open science is a bit wider than that, and we'll get to this. Another representation of open science is given by this diagram by Software Heritage. And it speaks of the 3 pillars of open science, which are on the left, open access to the scientific articles, then open source software, then open data sets. That is the repository where data sets are openly available. And the idea is that all research products should be open unless there are good reasons not to make things open. So that's the idea of as open as possible, as closed as necessary. There might be good reasons to not open your data or your software, maybe because there are some privacy issues, maybe because there is a industrial secret, and you're working with companies that has a patent, lots of different reasons. So there are obviously legitimate cases where you don't want to open things, but as much as possible, you should try to open things. The last point is also important, as early as possible. So the idea is that data and code should, as much as possible, be open, probably at the time you submit an article, even before. That's not a problem. So There are lots of discussions about that, and you may think, well, I don't want to publish my data too early because if there is something to find in my data, I won't be the first, and I don't want others to find things in my data before I do. And that's okay. But you can also say, okay, we can advertise the data. That is, I say, I have produced this data. I submit it, but not in an open manner. You submit it with an embargo. You can say, by the time I submit it, it will be, I will just make sure everybody knows that I have produced the data, and there is a third-party host that can attest for that. But you say there is an embargo, and I don't want the data to be actually public before 1 year from the date of its publication, or 6 months, or whatever. So that's a way of protecting your data, but still advertising the fact that they exist. You have produced them, you are the author, and you still make them citable. So people, you can cite them in your further work. So, okay, you see my point. Again, it's as open as possible, as close as necessary, and as early as possible, again, considering this whole questions of who could get the first good clue about your data, of your software, and so on. Okay, so this is the, say, the what of open science, but you may wonder why. Why we want to do this? What are the benefits that we can expect from this whole set of practices that are open science? And there are multiple claims about that. The first one, and we'll talk about it more extensively later, is the fact that it fosters reproducible research. That is the fact that other researchers may be able to reproduce and verify the claims that you have in the articles that you have published. And basically, this is a foundation of the scientific method. Okay. If you publish something, some results, well, other researchers should be able to verify that you're right. That's a part of it. And this is summarized in this sentence: non-reproducible research is not science. And this is maybe sometimes something that we tend to forget today in some respect. Another benefit of open science, the expected benefit, is to make scientific knowledge accessible to everyone, regardless of the location, institution, or financial resources. You know that some journals have very expensive subscriptions, and some universities cannot afford the cost of such subscriptions. And this is a real problem because it hampers the free circulation of scientific knowledge. What else? It's supposed to increase integrity. Yeah, well, if you share your code and your data at the time you publish your paper, well, presumably you wouldn't lie about what you've done because people will verify it. So the fact that your work can be reproduced by others forces you to be honest, scientifically, intellectually. It is also supposed to foster more effective collaboration across the researchers, across the institutions, maybe interdisciplinary collaboration. And as a result of that, this collaboration can increase the creativity. It's also supposed to accelerate scientific discovery and innovation, because basically, if your work is public and people can reuse it instead of redoing it, it's going to be much faster. And finally, it's also, well, finally, it's not an exhaustive list. There are lots of other things. I have selected a few of the arguments, but it's supposed to increase public trust in the science, in the results of science. And this is something probably very important, more particularly today, I would say, at the time where fake news and extreme right populism questions everything and every consensus, even scientific consensus. Well, making things very clear and very open, we can hope, can fight against this kind of movement. But anyway, to be fair, I've not seen any study that actually measures or confirms those claims. So you may wonder, okay, this is all good will, let's say, but is it actually true? If you take the ones on the left side, I would say it's pretty obvious that it will enforce reproducible research. Well, it makes things more accessible, obviously, and again, like I said, if you're transparent on your results and the methods, then it increases integrity. So I think that's rather clear. For the right part, the fact that it would increase collaboration, it would increase creativity accelerates scientific discovery. There is a large consensus about this, but to be honest, I've not seen any study that measures this precisely. So we can hope this is true. We can have some sort of faith in that. But yeah, there's no actual proof of these benefits. Anyway, the fact is that most countries now and institutions have a strategy for open science, and this can be seen. These are just a few examples. So from left to right, on the left, this is the UNESCO recommendation for open science. Then this is the Horizon Europe recommendations for open science. Horizon Europe is the European Union's key funding program for research and innovation. The third one is the French second national plan for open science. And the last one is from the American National Academies of Sciences, Engineering, and Medicine. And all of these restate what I've said here in more details about how to implement this in their own countries and institutions. But okay, there is a clear consensus, international consensus in that. And closer to us, this is the website that University Côte d'Azur has set up like less than a year ago, I say, which gives pretty much nice information. So it advertises trainings and master classes for students as well as researchers. And there are multiple good resources here about how and why you publish your articles in open access, what it means, about the different types of licenses that you can find, about how to store your data and write a data management plan, which is now a requirement in most of the French and European projects. What are the different types of identifiers like DOI, researcher identifiers, and so on and so on. And there is this barometer of the open access publication. So at the moment, 68.2% of the publications of University Côte d'Azur are in open access, which is a good one. Okay, so having said that, what can we do? What is the part that we as researchers can do every day? I found this taxonomy of open science. It's, well, to be honest, it's more a list of topics and keywords, maybe more a mind map than a taxonomy, strictly speaking. But anyway, it's an interesting map because I think it covers most of the topics that are related to the question of open science. So I will not go through all of those, of course. I will let you go there if you like. By the way, on this page, each of the titles here of the items are clickable, and then you can get a more advanced definition. That's pretty interesting. So I will focus on a few points. The first, where's my mouse? The first one will be on this big part, open access. And you know that there are several models of publication about whether your articles are open or not, or at which degree they are open when you publish. You may have heard already about the green and the gold models, or what they call here the roots. The green model is when the final manuscript is not open. That is, it is typically in a journal that has a subscription fee, but the author manuscript is open. And that's exactly what our institutions ask us to do. So whenever we publish an article somewhere, we have to put the author manuscript on HAL. The author manuscript is the camera-ready version before putting the copyright of the editor. So it should not contain any editor. If so, we are against the law. So you take the final manuscript without any copyright, and this is the one you're supposed to do. And this is the case for any article. There is no restriction, again, unless there are privacy issues, but in this case, you will not publish it in a journal. So I mean, there should not be any problem here. The other model, the gold route or gold model, is the case where the final manuscript is in open access, But then there is a fee that is paid by the authors. That is, you as an author, your institution will pay some fee for the article to be in open access. And that's not recommended. That's actually really discouraged now by our institutions, precisely because whatever happens, your author manuscript should be open access anyway. On how? So you always get back to the green model, and you should not pay to have an open access because you're going to make it open anyway. And this list forgets one that I have mentioned here, diamond route. Diamond is the case where there is no fee at all, neither for the authors nor for the readers. And that's the nice world of everything is free, but that actually exists. So at University Côte d'Azur, they have a service called Revel. And Revel is this service that is ready to host for you a journal or the proceedings of a conference, and it's all free, literally. So you can go to, if you organize a conference, for instance, you can go to the university and ask them to host the proceedings of the conference. It's going to be all free for everyone. Okay, and then I would like to go more on this second item here. It's about the evaluation of science. And this is a very important topic. How you evaluate things will condition how things are made later on. Or in other words, you get what you reward. The way you evaluate research is a key to drive the practices, that is to drive what people will do. If your metrics about evaluating things is mostly about quantities, is mostly quantitative. That is, if you count the number of publications and don't really care about anything else, then people will publish as many articles as they can, because that's what you measure, and you get what you measure. Okay. So if we want to go out of that model that has real drawbacks, I mean, hyper-publishing, hyper-authoring, these are things, these are behaviors that we would like to not see anymore. But if you want to do that, you have to reward publishing in another way. And that other way is that what you would get here. So there are different ways of measuring the publications, measuring the production of a researcher, of an institution. And in particular, something is called alt metrics for alternate metrics. And people try to think about new ways of measuring science, measuring the scientific production of researchers, so that what we incentive is not just the quantity, but also the quality. But obviously, measuring the quality is much more difficult than measuring the quantity. So there are actual very interesting works in this domain. In particular, here below, I have cited two initiatives. DORA is the Declaration on Research Agreement, and COARA, Coalition for Advancing Research Assessment. COARA is actually a later work that is based on DORA, on the principles. And DORA typically provides a set of recommendations for funding agencies, for institutions, publishers, and researchers about how to focus on more qualitative metrics than quantitative. So there are lots of works on this. You can check on COARA on DORA. There are thousands of universities that have now signed a letter of intentions of contributing to these new ways of evaluating science. This is really interesting things. And I think we as researchers should be concerned by this, because yeah, if we want to make things change, then we have to move on, and to move on, we have to acquire better practices, let's say. Just as an illustration, this is a slide that I took from a presentation given last year by Costas Grinos at University Côte d'Azur. And so this one illustrates the types of academic work that matter, or that matter most for the careers of researchers. And you see, without surprise, at the top is research publications. Okay. Now look at the last line, it's open science and open access. So that means for a researcher, focusing on open access or open science are the least impactful for their careers. which means that there is a clear problem in the way we evaluate the production of a researcher and how it impacts their career. So again, we have to reward what we want. And what we want is not just quantity. We want to reward quality production, but we want also to reward the production of good quality data sets that can be used by others. And for now, this is absolutely not rewarded. You can publish any data set you like, even the best ones. You won't get credit for that. That's a real issue, okay? To continue on this part of the evaluation, this one is interesting too. Open peer review. Maybe you've already seen this when you review some papers for conferences or journals. You can be asked whether you would like your review to be public in the end. Not only it can be public, but your name can be attached to the review. And I think this is a very good practice because it necessarily makes you take responsibility for the review. That is, I have written this review. I assume it. I take responsibility for that. I have no shame, which means that I have been honest. And we all have stories about reviews coming back and we say, come on, what happened? This is very unfair. The reviewer said this and this, but he didn't understand. And you never know whether this is because the reviewer did not understand your work or because they have another agenda that you don't know of. Maybe they work on some similar article and they want it to be published before yours. You never know about that, but you have this doubt. Well, if the reviews are public, that cannot happen because if you're really playing this game as a reviewer, it's going to be obvious. Another very good, interesting thing about open peer review is that to come back to the question of what we measure about the work of a researcher, well, with this system, you can get credit for the reviews you do. And so I've cited this study down here, which says that 20% of the researchers perform 69 to 84% of the reviews. So you see a small amount of the researchers do the biggest part of the reviews. And doing the reviews is part of science. We are doing peer-reviewed science, okay? Peer-reviewed publication. So since this is part of the job, well, we should be credited and awarded for that. And if reviews get public, then we can get into the metrics, the amount of time that you spend doing reviews, because that's how science works. So again, measuring what you want to incentivize, okay? The next step will be, focus I want to make will be about reproducible research, and that takes me to the second part of this presentation. Are there some questions so far? Do you want to share experience? Anything you would like to say? It's open, really. Yeah.
Between the green book and the code book, is there a difference in the manuscript except for the rights?
That's the only difference.
Okay.
Yeah. Maybe there can be slight differences about formatting because the editor in the end will maybe reshape your article in a way that's not exactly the A4. Yeah, but the text is strictly the same. The figures, everything is strictly the same. It's just the copyright. Yeah. Okay. So anything else so far? Okay. Okay, so let's focus now on the question of reproducibility of research and the so-called crisis of reproducibility. So there is existing debate about whether or not there would be such a crisis. Some studies say we have today a crisis, and meaning the research articles are less and less reproducible. There are studies that say the contrary. So to be honest, I'm not opinionated on that. Let's just say that there is debate and we don't have a clear answer. But nevertheless, there is the reproducibility is a very important subject and it's full part of open science. And this is something we should always keep in mind when we publish an article. So At first, let's make a bit of vocabulary clarification, because when you talk about reproducible research, you may see these different terms: repeat, replicate, reproduce, reuse. These are terms that are used differently in different contexts because there are, say, discrepancies in how people understand the words. Here I will present one of the definitions that exist out there. It's not the only one. In particular, the second and the third, replicate and reproduce, are sometimes switched in the definition. If you go to ACM, the ACM web pages that are dedicated to open science and reproducibility, they use the exact opposite meaning definition for replicate and reproduce. So just be aware of that. Not everybody agrees about the terms, but the idea remains the same. Okay, let's start with repeat. What is it to repeat research? Here, the idea is that we are going to repeat the same experiment, understand the experiment as being the set of scientific hypotheses that you want to test or prove. It's going to repeat it in the same setup, and the setup will be, in our case, usually the methods, of course, but also the software, the data that you're using to do your experiments. And it's going to take place in the same lab. And again, in computer science, when we say same lab, that usually means the same computing infrastructure. So whether it's on your own laptop or in a big computing node, whatever, but this is the whole experiment environment, let's say. Replication is similar. That is, you're going to replicate the same experiment. You want to test the same scientific hypothesis in the same setup. So basically, you use the same software data, but you will use it in a different computing environment. This is it. Reproduce will be about testing the same hypothesis, but maybe you will develop new software implementing different methods to get to the same result. And obviously, it's not going to be on the same environment either. So you see that this is increasingly complex when you move from repeat to reproduce. And the last step would be reuse, which is the ultimate goal that helps us go faster to test new ideas, new hypotheses. Maybe that can mean reuse some existing methods, but with different data, or reuse data, but in a different context to prove some different hypotheses and so on. Now, there is no strict boundary between those four terms, and it's more a continuum, and sometimes it can be pretty hard to know whether you are actually repeating or replicating, or do you replicate or do you reproduce? It's not always so clear, but okay, this gives you an idea of how things progress in terms of complexity. And in the context of open science, when you hear the term reproducibility, that basically refers to those three terms without clear differences between them all. Okay, so now that we've cleared some vocabulary issues, what is the problem really? What are we talking about when we talk about reproducibility? So you yourself may have been in this position sometime of a researcher trying hard to reproduce the results that is in an important paper that they want to base their work on, but it's hardly possible to do it. And you cannot do it because the paper doesn't give you any detail, the code is not provided, and the data that is used for the experimentation is not provided. And you have tried to recode the thing, to regenerate your own data, but you get to very different results. So what's going on? Okay. And how would you want to build upon these works if you cannot even reproduce the results? And basically why this matters so much, it's because an article necessarily contains, or no, like omits many details that you will need to reproduce an experiment. It can omit some important choices that you've made in the code about what is the architecture of your software, maybe what are the hyperparameters of your model. Maybe you've not said that in the article. What is the protocol of the study that you have used to do whatever you want to do? Maybe the method works with the author's data, but it doesn't work with your own data. So what does it mean? What should you conclude? Is it a flaw? That is it because the authors made a mistake? Or is it because maybe they forgot to say, oh, by the way, our method works in this very specific scope. And you are outside of the scope, but you don't know it because they didn't say it. Okay, so there are lots of things that you don't know just by reading the article. And for this, you need the data and the code. And if you don't have all of these details, it's hardly possible, again, to verify the results and to reproduce, and therefore to build upon the work of these papers. And there is quite some literature on this problem. And here I will point to a few articles. This one is from Nature. It has quite strong statements. First one, it says the lack of access to code and data is in prominent scientific publications may lead to unwarranted and even potentially harmful critical trials. So here they do not only say that it's impossible to reproduce work, they also suggest that it might have critical consequences. Okay? Making one's methods reproducible may surface biases and shortcomings to authors before publication. That points to what I was saying about the as early as possible. If you publish your data or your code early enough, maybe some other people will check it and detect some biases that you have not noticed or some bugs in the code. You don't know. And maybe they will save you the cost of publishing and having to retract your paper or modify and so on and so on. So sometimes we consider early publication as a risk, early publication of code and data as a risk. Consider it can also be very helpful. Yeah, what is preventing external validation of model will likely reduce its impact and prevent other researchers from using it to build upon. Reduce the impact, that means concretely to minimize the number of citations that you may get afterwards. So that's also something important to consider. Other examples of papers that talk about this problem of reproducibility, on the left side, this is in the domain of economics, and where they have made a study that shows that only 38% of the papers they have tested were successfully replicated. On the right one, it's even much worse. It's actually very concerning. So this one is from Molecular Brain, and the author is an editor who says that he's been handling 180 manuscripts during, I think it's the 3 years period, something like that. And among these 180 manuscripts, he sent a response for 41 of them to the authors, requiring additional to provide raw data, because it was not possible to judge without the raw data. Among the 41 articles for which they have required raw data, 20 of them were simply withdrawn. This is it. So you are asked to provide data and you say, oh, okay, I'll withdraw my paper. That's, you know, suspicious at the least, okay? For the 21 others or 20 others, 19 were rejected for insufficient raw data. Only one was accepted. So this is a very concerning result. There can be different reasons why people would withdraw their article, but you cannot do something else than suspect that there might have been some fraud, or maybe they have tweaked their result, maybe they have tweaked the data because it was not exactly how they wanted it to be. Okay, you can really think about it. Again, it doesn't mean this is always the case, but there are some studies about that, about the question of fraud, in particular in here in the medical research. So that's a concern. And again, the conclusion to that is that if we open the code and the data clearly, transparently, then that's a real good method to avoid this kind of issues. Last illustration, and then I think you will really get my point. You already have it probably. Maybe you know this website, Paper with Code. It's a site that lists articles and tries to reference whether the articles are provided with a code implementation. Actually, the site does much more than that. But in this specific page, they show the amount of papers that's specifically in machine learning that are provided with at least one implementation. The implementation might be either an official implementation, so coming from the authors, or a community implementation. And it shows that if you look, let's say, from 2019 to 2023 to December, so right now, it's been almost stable around 30%, which means that 70% of the machine learning papers are published without a single implementation. This is super worrying. Okay. And this is also, there might be a bit of noise here because what they explain is that they also include in their study some preprints. And we can consider, okay, some preprints maybe deposit on archive before the authors have published an implementation. Okay, that's possible, but still, it doesn't explain this huge number of papers that do not have code. Okay, so you get my point about the question of reproducibility. And in the end, why we need to do that, why we need to publish the article code and the data all together and link them together. There are several reasons to that, which are quite related to the reasons for doing open science that I was mentioning at the beginning. One is that my research most of the time is funded by public grants, and since the article is supposed to be public too, because of that, well, any other product of research should be public too. That includes data and software. One thing is that if I publish all of that together, that is, if my article links to the code and links to the data, well, as a reviewer, I would be tempted to say, okay, that seems serious work, that's transparent. And I can go and check whether the implementation seems sound. I can even try it sometime. Okay. So that should help in the review process. What else? Well, of course, it can help people use my algorithm, compare it with others without having to re-implement it, which means that I would possibly get more citations, because if people can reproduce my work, they will use it as baseline, and if they use it, they will cite it. Okay. Oh, sorry. And indeed, there are some studies that show that there is a tendency to increase the number of citations of the papers that do provide either the code or the data. And down here, this is a study that dates back to 2020. It's not about code, it's about the data availability. And they show in the corpus of articles that they have studied, they show that those papers with a data availability statement that contains a link, so you don't just say data are available, but you point to the data clearly, those papers get up to 25 higher citations. I think it's 2 years later, something like that. So, okay, we can suppose it has an impact. To be honest here, if you go back to the slide I was showing here on the left, this was in the case of economics. And if you look here at this sentence, it says replicable papers do not provide citation bonus for authors. So it is not so clear. Maybe it depends on the community. Maybe it doesn't have such a large impact in economics, and it have more impact in computer science. I don't have the explanation here, but it seems to be the case though. And finally, that's a personal assessment, but I think opening code and data tends also to improve the quality of the work overall. The idea is that if I need to share my work, if my code is a quick and dirty notebook, I will not dare share it like that. So I will do a bit of work to make it look nicer, more documented, maybe more reusable in a different environment, commented, and so on. And same thing for the data. You cannot publish data without giving explanation, metadata. That is the metadata that explains you how to understand the data. If you publish a CSV file and you don't say, you have 100 columns and you don't say exactly what each column means, and in this column there are figures, but what is the unit of the measures? If you don't know the unit, okay, you see my point, this is useless. So sharing things forces you to make things more good looking, and overall it will probably improve the quality. Okay, so we've seen the reasons for opening code and opening data, good on that. But after all, that's something which is not free. It has a cost. It's time consuming. So what are the incentives for doing so? The thing is, today, there is no clear movement for journals and conferences to require that you publish your code and your data along with the articles that you submit. It's not yet a requirement, but there is a clear uptake towards this direction. And here are a few illustrations that I have found. In some conferences now, as a reviewer, you can have a checklist, and a part of the checklist can be about the reproducibility of the work. So this is the case for those conferences, not the least like ISHCAI, okay, major conference in AI. So reviewers are encouraged to look at, to assess the availability of the code and data, and to give an idea of whether or not that seems to be reproducible. They are not asked to reproduce the things. Of course, it would ask a lot of work, but at least they should give their opinion about whether the work seems feasibly reproducible. Now, in many conferences, you can find reproducibility track. So when you submit a paper to a research track in a conference, you can also register to the reproducibility track saying, okay, I'm confident enough, and I think my work is reproducible. That exists in some conferences, not every time. That is, I have seen some conferences that were doing this 1 year and not the year after, and again the year after. Probably the reason is that doing this really requires a lot of work, because these are third-party people hired by the conference who will try actively to reproduce the work, and sometimes that can be a lot of work to try and reproduce. So it's not systematic, but that comes. So I think this will be more and more the case. I hope so. There are some editors that are clearly moving towards this idea, and here this is the ACM Digital Library. They have developed this, what they call the active digital curation platform. Basically, it's close to the concept of executable paper, and they provide a lot of guidelines about how to make your work reproducible. And this is an editor, so that's quite a sign. And similarly, you have more and more conferences or journals that provide different stamps about the quality of how we think your work is available, reproducible, and so on. For ACM, you have a list of colored badges for available, functional, reusable, reproduced, and replicated. And this other one, replicability stamp, is in one specific community, in the graphics community in computer science, but they have their own replicability effort too. So again, doesn't mean this is a generalized effort, but you see that things are moving in this direction anyway, I think. Okay, so what about the incentives that we have? And to continue now, specifically on the case of the data, some journals implement what they call data availability policy. Here I have listed some of those. In Springer, for instance, Springer has edited a set of 4 different policies, and you can see that they go from simple encouragement to a requirement. The first one I cite, Springer Scientific Data, says that the policy is data sharing, evidence of data sharing, and peer review of data is required. Well, it's normal. Springer Scientific Data is a data journal. So obviously, when you publish a data paper, you should be required to provide the data. That makes sense. The other ones, it's in the humanities, data sharing is encouraged and statement of data availability required. The next one, Cell Discovery, is a journal from Nature. They have reused this last policy from Springer, and here the 3 ones or other I have found here and there in different domains. So you see that most of the journals now tend to have a policy about data availability. Okay, so now we see some of the incentives, all right? But it looks like some people tend to tell us, okay, go ahead and open your data, open your code at the same time you publish your article in open access. So I have incentives, but do I have some rewards? Because that's the thing. If you really want people to do things, you have to reward them. Okay, it's the carrot and the stick. And if you wonder, this is the dopamine molecule, which is the dopamine that your brain secretes when you get some reward. And the first thing you may think of when you think about getting rewarded for opening your data, for opening your code and your articles, is to have a regular paper. And this is one way to do that. So there exist data journals where you can publish a data paper. The data paper, it's basically a more compact and light type of article where you will describe your data set, the way you have processed it, the way you have, I don't know, debiased it, and so on and so on. And it is a peer review process. Same thing for the software. It's more rare now, but there starts to be some research software journals where you can publish a software paper. That's the same idea. In the conferences, more and more commonly, you can find some resource track papers or resource tracks. And the resource track is typically where you will publish an article about a resource. A resource could be typically a data set that you have compiled, or a software that you think will be useful for a larger community. So all of the three things are a way to have your data and code rewarded, because this is a paper. These are actual peer-reviewed papers, so they fit into the existing framework of citation. They fit into the computation of your H-index. Okay. And here are a few examples of data journals on the left and the software journals on the right. So you see it's more and more common. And you can do it, and again, it's not very expensive. I mean, data, whether it be a data paper or software paper, it's going to be peer reviewed, but it's not such a hard work compared to a research paper. So really, you can try this. If you have a good data set or a good software you think is useful, go ahead. Okay, so here what we do is to tweak the things. That is, we don't make data or software citable. We create articles about data and software. But what we would like in the end is to cite the data and the software themselves, not papers about the data and the software. Not that it would be bad. I mean, if you cite data paper or software paper, that's okay. And in some cases, there are good reasons for that. Basically, in a data paper or software paper, you may provide details that do not exist in the code itself. You may provide an assessment of the performance of your software, which is an added value to a paper. So there are also good reasons for papers, or about the data paper. That can be good reasons because you provide some information about how your data set is balanced, and if you have done some debiasing and so on and so on. But if we consider the more global scope of research reproducibility, we don't need just citability. We need no more than that to make things reproducible. And for that, that's what I have called it FARC, like findable, accessible, referenceable, and citable. This is the properties that we need to enforce on our data and our code. So first of all, this acronym FARC, I made it up. So do not communicate around with this going, my code is FARC and blah, blah, blah. No, it's not going to work. But so obviously it's an analogy with FAIR, the fairness I mentioned at the beginning, findable, accessible, interoperable, reusable, which applies specifically to data. The thing is that findable and accessible work pretty well for code. Interoperable, okay, that works for data, I understand it, but what would it mean for code to be interoperable? It's not pretty clear. The R, which is reusable, I have, well, an understanding of what should be a reusable code, but how to measure that? Is there any actual formal specification of how we would measure the reusability of the software? It's unclear. I don't know of maybe there are some such works in the software engineering domain. I don't know. but it's not been formalized the same way it's been formalized for fairness. So let's go through these 4 terms. The findability. So here, this is going to be the same thing as for data. The findability is a property that you can reach with by providing rich metadata. So which metadata? That's going to be, of course, the title, the authors, publication, release dates, the version, the license, which is very important, the provenance information, if any. Maybe your data set is derived from another data set, so you should have this provenance tracked into the metadata. You need a persistent identifier that I will come to this specific point just after that. And these metadata are typically what will be in a data portal on or a repository where you could do some search either by keywords, by facets, and that will help you find what you want. So that's the idea of findability. That's why metadata is necessary. Accessibility is the property of your data of software to be not only available right now at the moment you publish an article, but to be available in the long term. That is, it's going to be hosted in a sustainable system, and you will have the ability to find it in a number of years from now, and it's still going to be available. Citability, we've talked about it quite a lot already. This is about giving credit, so to attribute the work to someone and to cite it in some papers or to refer it from other works. And referenceable is slightly different from citable. Citable is just a citation like you would do in an article. Referenceable means that you can point to the exact specific version of the data of the software in this whole development history. So citability is important to keep track of the things, to give credit, but referenceable means that you can also get back to this exact same environment and reproduce the experiment, which is not the same as just citing things, okay? And at the center of all of this is this thing here, the persistent identifier. And I've named it like that. PID is all you need. So if you're doing natural language processing, you will get the joke with attention is all you need. If not, no problem. But the idea is that the persistent identifier is something that's needed for several purposes. First, it helps you name the resource in an unambiguous manner. It makes it possible to associate metadata to your resource because you have named it unambiguously. You can use it to cite the resource, and you can use it to reference to a specific version. Note that the persistent identifier that you cite and the one that you reference may not be the same. You can cite a data set in its globality or a software in its globality, but you can reference to a persistent identifier that identifies a specific version of it, which may not be the same one. So there might be multiple persistent identifiers for a data or for a software. It's not a problem. Okay, so let's get into more concrete examples of how we can make things FARC, starting with a C for citable. So the first thing, most simple thing you can think of is to add citation guidelines to the landing page, basically, of your data, of your software. This is an example of a GitHub repository about a data set we have published. And here in the README, basically the README that you have on the landing page of this repository, I have explained how I want this work to be cited. In addition, I have a reference down here, which is a regular article. And like I was saying, you could have citation guidelines for your work, for your data, but you can also add some information about an article that mentions your data or that describes your data. It can be a data paper, it can be a software paper that's not incompatible. So this is fine. This way, you just give other humans the way you want your data or your software to be cited. But there is one drawback, is that it's basically for humans only. So we would like something more machine processable, right? And for that, well, there actually exists a format which is called CFF, for citation file format. Basically, it's a structured format that you can use to provide different information about the authors, dates, license, repository, and so on. and that's going to be interpreted by other software, other platforms. So here is an example of how it looks. It's basically a YAML file. And down here, you have a link to a form that can help you generate this file. You can then modify it manually if you like. And basically, it gives most of the information you need. Like I was saying, the license. In this case, this is a software, so there is a version, there is a release date, and so on. And actually, maybe you've never heard about this CFF format, but it's pretty well adopted already. And it's supported in particular by some services like GitHub, Zenodo. If you're using Zotero, Zotero supports this file in their browser plugin. So when you browse a web page and Zotero detects the CFF in this page, it can use the CFF to generate the citation that's going to be added to your Zotero database. And here is an example of how it looks here. So I told you this is, where's my mouse? Sorry. So this is on a GitHub repository, and on the right of that, my GitHub page, there is this link here, cite the repository. This button appears only if there is a CFF file, and it gives me exactly the string that I need to cite that software, and I can have it in BibTeX if I like. So this is actually used, and you're going to see the same thing in Zenodo and other ones. Another one I will mention, Software Heritage. So, okay, so now that I can make things citable, what about the other letters? So how do I make my data findable, accessible, and referenceable? Well, the thing is, I need to publish my data somewhere. And for that, we have, in France, we have several solutions like data.gouv.fr and the subsidiary of this platform, which is recherche.data.gouv.fr, which is actually an outcome of the second National Plan for Open Science. It was a requirement from this plan. And this repository this is what it says. It's to be used when there is no well-adopted domain or community-specific repository. So you can use it basically whenever you don't know where else you could put your data. But actually, if you go in the details on this platform, you can find lots of spaces and collections that are for your institutions or for your lab. So there are collections for University Côte d'Azur, INRIA, CNRS. There is a collection for I3S, which is a part of the CNRS space and so on. And it's free. I mean, you can just log in and deposit your data. You have a set of metadata to enter, and the more metadata, the richer it is, so the more findable it is. And this is it. There is just a review process, and the next day it's online. And you have a DOI. Every deposit gets its own DOI. There are other either research or general purpose repositories. Here I mentioned Zenodo, which is maintained by OpenAir, and OpenAir is the European infrastructure that supports open science. Same thing here for Zenodo. Every time you submit a data or some software, you get a new DOI, and this DOI is citable, and the storage is supposed to be sustainable. So it should be there in many years from now, hopefully. Similar thing, Figshare, maybe you know it to deposit your slides or things like that, but actually Figshare allows you to deposit any kind of research object, be software, data, whatever. Maybe just one element of concern here. Figshare is hosted by Digital Science, which is a subsidiary of Springer Nature, which means it's a private initiative. That means you don't really know what can happen in the future. So if I have a choice, I'd better go to publicly hosted initiatives. And then Internet Archive, which is well known for archiving the state of the web, in particular the Webpack machine, but it allows you to store any kind of thing, and you can upload your data too. And what you will get is not a DOI in this case, it's an ARC, but it's also a persistent identifier anyway. And what else, if you want to move to some, well, if you are looking for some more specific, maybe domain-specific repositories, you can go to those websites, Re3Data for Registry of Research Data Repository, or Open Door, Directory of Open Access Repositories. These are two really good resources. They list thousands of repositories where you could deposit your data. you have some faceted search options, so it's pretty handy. And basically, these initiatives, whether those ones or the one I was mentioning before, they address the three concerns about FARC, which are findable, accessible, researchable. Findable because since you have to fill in a lot of metadata, your dataset or your software becomes discoverable. Accessible because they are supposed to ensure a long-term preservation. And referenceable because they give you some DOIs, so persistent identifiers that you can use, and that can be assigned for a specific version of a software. Now about the code. So if you want to share your code, the first thing you would think about is usually to store your code on a CVS, a code versioning system. And that's pretty nice. So you could use GitHub, for instance. You could use GitLab or a GitLab instance of your institution, Bitbucket, Redmine, and so on and so on. That's okay, and that's usually what we do. And in the article, what you give is a link to the GitHub repository. But remember that GitHub is a private company, and even if it seems super sustainable, you don't know what may happen tomorrow. So remember Google Code. Google Code lasted 10 years, and then that was over. And at the time, we were thinking, oh, come on, this is Google. It's going to be there forever. Well, no, in the end, no. And now you can find, there are lots of papers with links to Google Code that are just broken links. And you don't even know if the software has been put somewhere on another place. So it may not even be accessible anywhere anymore. You can also use other repositories like the ones I've cited, Zenodo, Figshare, Internet Archive. They are also good to store code. That works the same way. And I will make a specific focus right after this on software heritage and how. But before that, just a word about GitHub, because well, many of us do use GitHub. Know that there is a way to configure your GitHub repository to do an automatic deposit of your code on Zenodo and Figshare. On the case of Zenodo, that's pretty easy. You just log into Zenodo with your GitHub credentials, and then you have the list of your repositories, and you just activate the deposit for the ones that you want to store. And basically, what happens is whenever you issue a release on your GitHub repository, you make a new release, it will store a snapshot of that on Zenodo and assign a new DOI to that. It's as simple as that. And really, that's super easy. For Figshare, there's just a bit of hack to do, slightly more complicated. There is a hook, git hook something, but it works pretty much the same. So that's very easy to do. And again, it gives you instantly a DOI for your code. And it's much better to cite a DOI than to cite GitHub repository, GitHub URL. Okay, so let's go to software heritage. Are there some of you who know about software heritage? Maybe some of you who used it already? Anyone? Did you hear about it? No, no one? Okay. So software heritage is something you really need to consider. This is probably the most sustainable initiative in terms of code, long-term preservation of code today. Initially, it's been started by INRIA in 2016. Today, it is an open non-profit initiative, and it's been, I don't know when exactly, there was an association with the UNESCO. And since then, they have built a sponsoring model, and among the sponsors, there are most major public institutions, French or not, and a few private actors like, I named just a few of them, Microsoft, Huawei, Intel, GitHub, Google, Hugging Face, and so on. So you see that's pretty big. So it's very likely to be the most sustainable initiative for long-term preservation of code today. Just to give you an idea of the volume code that they host, this snapshot dates back to last week. They had over 18 billion source files almost 4 billion commits and 289,000 projects. So that's absolutely huge, really. One good thing about software heritage is not only they store and preserve software in the long term, but they also give you a way to cite software. And they have come up with this identifier called SWID, the Software Heritage Persistent Identifier. SWID is the result of quite a long work between several institutions, common work, let's say, between Research Data Alliance and FARC 11, which has long-lasting work on this domain. The idea of the SWID is to provide an identifier that they call intrinsic, as opposed to extrinsic. Intrinsic identifier means it doesn't need any external register for resolving. So what happens is that a SWID is basically computed solely knowing the project, the code, either the file or the project, whatever, or the repository. It's basically a hash. That's all it is. So what you need to know is the project, software project, and the algorithm to compute the hash, but this is it. I mean, you do not depend on an external service to resolve the identifiers, like DOI, for instance. DOI works because there is DOI.org. But if this fails, you do not have any resolver system worldwide for DOIs. Here, that's not the case. So you have an identifier that can last forever because it does not depend on any resolver. And that means you can develop a new resolver if you like. Because you know how the hash is computed, you can always get back to the initial code. And that's what they do, actually. They also provide a resolver system, which is this archive.softwareheritage.org. You just append the SWID, and that gets you to the landing page of that repository on Software Heritage. But that could be another one. I mean, it's not the only one. So typically, you should not cite a URL with archive/softwareheritage.org/SWID, because this links you to a specific resolver. The only thing you need to cite is the SWID. It's it. Another good property of the SWIDs is that they're able to reference a precise point in the history of the software development of your repository. Not only release, but you can reference to any commit and any file within a commit, and even any line of code within a file within a commit. So it's super fine-grained. So it goes from the whole project to a single line in a certain version. It's super flexible. Okay, and so you've seen the volumes of the 14 billion source files that they have right now, and basically that comes from one part is the automatic harvesting of some existing repositories. Here is a list of them. So that means GitHub might be somewhere in here. That means your code might already been on Software Heritage, or maybe not. And if not, you can just submit a request to Software Heritage to harvest it, and it's going to be pretty fast. And for some other repositories, they do an on-demand harvesting. So about GitHub, I mentioned there is this way of harvesting, of having your code harvested by our snapshot to Zenodo, and you can do the same thing to Software Heritage. But there is a big difference. If you get the URL of your GitHub repository, you submit it to Software Heritage. Software Heritage will not do a snapshot. They will harvest the whole software history. They have the whole history, including all the commits, all the comments, and everything. So it's the full software development history, which is a big difference. And there is also a connection with HAL, and I will come to this right after here. So you know that HAL is the platform where we are requested to store all of the articles that published. Actually, that can be more than articles, that can be preprints, that can be research reports, whatever, big documents. Actually, HAL is also the place where we can ask to store software. In fact, when we do that, we do not store the software precisely in HAL. We just reference it in HAL, but it's going to be stored in software heritage. So here is how it works. The most common case for us, let's say in the computer science community, we usually have our code hosted somewhere on a code versioning system, GitHub or GitLab or Bitbucket. What you do is you submit the URL of your repository to software heritage. Software heritage will harvest the whole content of your repository and issue this thing, which is the suite. That's how it looks. That's a big hash. Okay. Then either you stop here, or you say that, well, according to our institutions, we should also have a HAL ID for all of our research products in France. And in that case, you go to HAL and you submit the suite. Basically, you still have to submit a bit more metadata, but most of it will be harvested from software heritage. So it's mostly all automatic. And HAL will harvest the thing and store locally all the metadata. There is a moderation process. And in the end, you get a HAL ID along with your software, which points back to software heritage. The advantage here is that you can also create links between deposits. That is, you can link a deposit of a software to the deposit of an article. And you say, this article references this software, something like that. So you can create the links instead of hoping that eventually they will be discovered by some automatic process that is still to be proven. Let's say it this way. Okay, and the second option that I think is less likely for us, but it can be helpful sometimes, for those who have their code directly on their laptop, typically, and you have never stored it anywhere on a code versioning system, which should be a bad habit, but it happens. You can submit this directly to HAL. HAL will create a HAL ID, and it will submit it to software heritage that will create a software, the suite. So in the end, it's always stored on software heritage. So there is a close collaboration now between HAL and software heritage. Okay, and how you would do that? Well, you have a bit of work to do before that can happen. That is, before the HAL and software heritage can talk together, there are a few requirements about how you should prepare your repository. This is no big deal. So I'm not going to dig into those details right now. This is explained in the next slides. I will skip them, but just go back to the slides if you like. It's not really complicated. You just have a few files, those 4 files basically, to provision and to make sure they are here and properly formatted. So let me just skip that and just coming here. One thing you may notice if you do that, it's sort of a bit boring still today, because you feel like you repeat the same information again and again. So you will create a README, which is for humans, where you will say who are the authors and what is the current version. And then you have either a file called authors or another one, which is datasite.cff that I mentioned at the beginning. And then the CFF file, you will use the form to create it, where you will fill in the authors and the license and the version and the date of release again. And you will start, and then you will have the license file itself, and then you will have this code meta.json file, which is a standardized file for repositories to communicate with each other, for them to exchange metadata. But you have to do it again and again. You will enter the name of the authors, the name of the software, the license, blah blah blah. So it's a bit boring. It's no big deal. I mean, you do it once and that's done. Just know that I hope in the future it's going to be much more automated than that, because we can definitely improve the process. And this is ongoing. I mean, there are some people working. I have communicating a lot with some people from HAL, trying to understand some things. Maybe sometimes they have solved some existing bugs and so on. So this is moving. And when you do that, maybe it will have improved. I don't know. Okay, so if I get to the first solution I mentioned, you have your code on GitLab, Bitbucket, GitHub, whatever, and you just want software heritage to harvest it. You go to software heritage, enter the URL of your repository here and click on save. And this is it. And if in a few minutes from now, it's going to be harvested. And once this is done, here, that's the software heritage page. That's the original link, the URL of my repository. And here you can see that you can select any tag, release, or commit in the development history of your software. And when you do that, you can go to permanent links, and that's where you get this suite. So here I click on revision, and this is the suite of this exact revision that corresponds to the version 0.5.3 of my software. And that's exactly the thing that I want to cite in an article, for instance. If I have done something using this software, that's what I want to cite. Instead of, again, citing a software paper, I want to cite the software itself. You can have a bit longer suites if you include additional contextual information. That becomes a bit verbose, but it gives you the original link. It gives you a visit must be a hash of the date you visited it, something like that, or the date it was visited by software heritage, something like that. But not always necessary. I think the first part, the first line is the most important. And as I was saying, you can point to a specific few lines in your code, you select the lines, and that you get a suite specifically for those lines in this version of the software. So you can really get down to the fine grain. Okay, so here I have tried to go through the whole scope of things that we can use to have our data and software be findable, accessible, referenceable. Okay. Referenceable meaning we can store them in the long term and make sure we have a way to cite a proper version of the software or the data. Now let's take the things the other way around. How do I do to cite the work of others? That is, to cite or to reference the work of others. That is, to cite a certain data set, to cite a certain software. That means I want to give credit. So in my work, I have used the work from someone else, or maybe my own work, my own software, or my own data set, and I want to cite it. So I want to give credit for that. The first place where you could want to go is to DataCite, which is quite a huge initiative with lots of partners. It's a global community, well, say a global community of organizations and researchers identifying and citing research outputs and resources. There are lots of services on DataCite. It's not about data only, it's about any kind of research outputs. So it can be about articles, code, and any possible other artifact that can be produced by software, by research. You can go there to find data sets of interest. Maybe you can look for any kind of thing, like they have a metadata management system, they have discovery system, they have APIs and so on. And in particular, they have a citation format that can help you format the citation of the software or the citation of the data. Yeah, just a few more details about the internal, the whole structure of DataCite. In particular, they harvest existing repositories like Zenodo that I mentioned, or Crossref. So all of these repositories tend to harvest each other. You don't remember, sometimes you don't really know who's got the original information or not, but overall, you get a lot of information, all of those things. Okay, now let's get to more concrete things. And you write an article in LaTeX, and you want to cite a data or a software. How would you do that? Well, there happens to be an extension, an entry type, which is called dataset in BibLaTeX. So here is an example. Here I'm on Zenodo on a dataset, which is, again, lost my mouse. Okay, it's here. A dataset called COVID on the web, and I can ask Zenodo to give me the export in BibLaTeX. So you see this is an entry of type dataset. And if I do that and I cite it in article, it will look like this. So I will have the DOI, I will have the full URI, version, authors, and so on. Okay. So that's what I wanted, right? The problem, in my experience, I have tried it with maybe 5-6 different templates. It only works in LNCS templates. In all the other ones I've tried, that is the templates of the editors, either in conferences or journals, whenever you switch from BibTeX to BibLaTeX, well, it screws everything up. So unless you're a super expert in LaTeX and you can fix that, I can't. That doesn't work. So that's honestly, that's a pity because we have anything we need. Same thing for the software. There exists a software BibLaTeX extension of BibLaTeX with several data types, software revision, software module, code fragment. Here I give you the way to include it. And again, it worked in LNCS. And here is how it looks. So this is an entry of type software in which I'll list the suite in this case. So yeah, it supports HAL ID, suite, DOIs, ARCs. It supports lots of different types of persistent identifier. Here I use a suite. Oops, sorry. And this is how it looks. So here I have the software license and the suite. Here I create a second entry, but with the DOI this time. And here I create a software version entry that cross-references the software entry and adds a suite specifically for that version and not the whole repository. So you see that you can use citation to reference. That is, you can cite a whole project in itself or cite a specific version or a specific commit of that project if you like. And that's how it looks. So you may feel like, okay, that's a very, very verbose identifier. That's right. And that's a problem if the references are part of the number of pages you're allowed in your article. But if the references are separate, you don't care. You just cite things and there are as many pages for references as you like, which should be the case. Okay, so like I said, again, this one worked for me only with an LNCS. I have not tried all the templates there, but enough to see that editors don't make a big effort to support this kind of thing. And so the first conclusion is we have to yell at the editors, support those BibLaTeX entries. That's as simple as that. I mean, they just have to update their templates. And then we have a way to cite data and software directly from articles, and we have an automatic processing of that. So we know exactly, I mean, we don't need to do some PDF exploration, trying to figure out what is this the name of a, no, you have the DOI, you know it's a software. We have everything we need. We just need the editors to do the job of updating their template. If not, you still have to do with that. So what I'm doing usually is this kind of workaround. I use BibTeX because I have no other choice. I take an entry of type miscellaneous, and I use the note field like this. I said, this is a software, this is the version, and this is the suite, or this is the DOI. This is better than nothing, but definitely not satisfying because as far as I know, this is not machine processable yet. So there cannot be automatic extraction of this kind of thing because it's not standard. But I believe this is better than nothing. Okay. All right, we're almost at the end. So yeah, a few takeaways. At the beginning, we talked about open science in general, and this sentence summarizes it. Open science is science that's done right. It has 3 pillars: open access to the scientific articles, open data, and open source code. The openness is also something like a cultural shift in the mindsets. There are many people, many researchers, maybe if you're a PhD student, your advisor don't really care about opening software, opening data. You have to change their mind. That's all new because many of them really don't care, and the only thing they care about is articles because, again, you get what you reward. And if this is the only thing you reward is the publication of one article, that's the only thing you will get. Okay, but this is not reproducible research. To do that, you need to make your code and your data findable, accessible, referenceable, citable. You can store your data on research.data.gouv.fr or Zenodo or any other domain-specific repository that you like. You can store your code on software heritage, NHAL or Zenodo, NHAL, whatever. You just need a bit of work to prepare your repositories and to provide rich metadata. That's the only thing you have to do, but that's something you do once, and that's over. The persistent identifier is at the central point of all of this because it helps you name the resource, cite it, reference a specific version of the resource, and that's how you associate metadata to the resource. Now, like I was saying, there is still a long way to go, long or not so long. Maybe it could be short if people do a real effort. So one effort is to be done by the editors and the need to support data and code citation. First, I mentioned it, they have to update their template, their LaTeX templates, so that we can actually cite data and code. It's as simple as that. Something else is, I mentioned that the size of this PID, the suite can be super long, and maybe you don't want to waste some space if your article, if the number of pages of your article, the size, the limit includes the references. But if we want people to cite data and code, then we should take the references out of this limit, give a number of pages for the article itself, and do not limit the number of references that you can provide, because otherwise people won't cite things. I mean, if a citation takes that long, it takes 10 lines, you will not do it because you don't want to waste time for something that will be in your article instead, of course. So they have to do that job too. And again, nobody does paper edition anymore. This is electronic edition. So we don't care how many pages for references there are. We need a way to track the relationship between an article and the code and the data. And this is not there yet. There are some portals that now provide some metadata to do that, but this is not so satisfying. I mentioned HAL. You can do that, but it's not really sufficient. For instance, you can say an article references a software. Yeah, but for what? Is it because the article describes the software? Is it because the article reports on the work that used a software? This is not clear. So we need to have more semantically rich associations between article, code, and data. And that's just a matter of agreeing on the list of properties to describe those relationships. It's not more complicated than that. And then, yeah, about the reward part, we get what we reward. So we need to have ways to credit and reward what we want to favor, what we want to incentivize. So we need to that. For that, we need to change the metrics so that we would reward impactful software, impactful data. If your data set is super interesting and has been used by lots of people, you should get credit for that and you should get rewarded for that. And for now, that's not the case. This is not okay. So rewarding reviewing work, I mentioned it about with the process of open review, which is really interesting too. And if you spend a lot of time reviewing the articles of others, you contribute to the science and you should get rewarded for that. And then again, there's a lot of work to change the mentalities, and that probably is what takes more time. And I think I'm done. Oh yeah, just one more. Remember I mentioned Dora and Koara a few slides back. Go there if you want some clarifications about this whole question of how we measure the impact of science, how we measure the carriers of researchers and so on. They have really very good insights into that. Thank you very much for your attention.